So welcome all to week 6 tutorial for the course Essential Mathematics for Machine Learning. I'm Pintu Kumar. I'm a PhD scholar at IIT Bombay. The topics that I plan to cover today would be classification metrics. So here I'll talk about all things related to confusion matrix and then your F1 score, and then also I'll try to motivate these whatever you have learned in this lecture for multi-class classification, because multi-class classification is sort of important these days. Okay. Then we will go to something known as Gram-Schmidt orthogonalisation process, where we will learn how to convert, if you have a basis available with you, then how do you convert it to an orthogonal or an orthonormal set of bases. Okay. Then towards the end, we will look towards some problems based on Jordan canonical form. And yeah, we will also look a little bit about normal this polar decomposition. Okay. So during any time in the lecture, if you have any doubt, you can either unmute yourself to speak, or you can type it in the chat box. In any language, Hindi or English, both is comfortable to me. Okay. Okay. So if you look at the kind of tasks we have talked about earlier related to machine learning, in the last 2 weeks, we were talking a lot about classification. Okay. Now, we also talked about logistic regression in our previous lecture. So once we have learned classification, so you want to check whether your model is good or not. Okay. So you want to check how good or bad your model is performing. To check the performance of your model, you use something that is known as classification metric. Okay. So what does classification metrics gives you? It gives you a measure of how good or bad your model is. Okay. So let's say, so you have a classification task. Okay. And you trained your model on some data set. Okay. Then how do you check the model that you have learned is good enough or not? Okay. So what you used to do, you used to test its performance on test data set, right? Okay. Now, how do you quantify this testing of performance on test data set? That is given by classification metric. Okay. One very simple or the most intuitive way is that something known as accuracy. Can someone please confirm my voice is clear, right? This noise is not making, this fan is not making noise.
Yes, sir. Clear.
Okay. Yeah. So first thing is accuracy. So what is accuracy? Let's say you had 100 points in testing data and you made correct prediction on 80 of them. Okay. Then accuracy is given by the number of points where you made correct prediction divided by total number of points where you are checking your prediction. Okay. So this is quite intuitive, right? So this is something that is known as accuracy. So accuracy is nothing but number of correct prediction divided by the total number of predictions that you're making. Okay. So this is the accuracy, and accuracy, although it is not a very good measure for imbalanced data set, but is sort of very much used even today when you're reporting your performances. Okay. So generally you will find accuracy in percentage that you can obtain by multiplying it by 100, right? So this value will, this formula in the purple will give you value between 0 to 1. You can multiply it by 100 to obtain your percentage. Okay. So if somebody is saying that it is 90% accurate, that means it is making correct prediction on 90% of the test data. Okay. Okay. Now consider a very simple situation where you have a classifier. Let's call that classifier as F. What is this classifier doing? This classifier is assigning every data point label 1. Okay. So you have a data set with two labels, that is class 1 and class 2. Class 1 has 1000 points. Okay. And class 2 has 100 points. So you learned a classifier, let's call it F. What that particular classifier is doing, it is saying that it will assign every data point label 1. That is, it will map every points to class 1. Now, as you have 1000 data points of class 1 in your testing set and 100 points of class 2, what is the accuracy that you will obtain for this thing? So accuracy is as mentioned above. So first you have to write how many points you made correct prediction. So as you are classifying everything as class 1 and there are 1000 points belonging to class 1, so for these 1000 points you are making correct predictions, right? So the number of points where you are making correct prediction is 1000. And what is total number of points on which you are making prediction is 1000 plus 100, that is 1100. So what is this value? This is something 10 by 11. If you will find, I think it will be approximately equal to 90%. So if somebody says that his model is performing 90% accurately, then it sounds like great, right? It sounds like that his model is doing very well. But if you look at this classifier, it is making almost like it is making 100% error when you have to classify class 2 error. So in reality, this classifier that you have learned is very bad, right? But if you calculate its accuracy, it's getting around 90%. So what the problem over here is, so whenever you have data set for classification and you have a large number of data points belonging to one class and small number of data points belonging to other things, that kind of data set is called imbalanced data set. Okay. So for imbalanced data set, accuracy is not at all a good measure of not a good classification metric. Accuracy is not a good classification. So what we will do, what we will do is, we will try to define some classification metric that works well with imbalanced data set, right? So two of them are something known as precision and recall. Precision and recall. And then we mix them together to form something called as F1 score. Okay. So any doubt till this point in accuracy part? Okay. So before going to micro F1 and F score, what we can do is we can construct a matrix called as confusion matrix. That matrix also sort of gives us some idea about how well we are doing on our classification task. Okay. So let's say now you have two type of data points. One is positive, one is negative. Okay. So you have two kind of data set. One is positive, one is negative. So you create a matrix. So let's say this is your actual label and your rows or this side represents the predicted label. Okay. Now let's say you have two classes, that is positive and negative. What would come in first class, this is known as this first position, this is known as true positive, that your actual label was positive and whatever you have predicted, that is also positive. Now if you count how many such data points are such that their actual label was positive and the predicted one is also positive, that gives you the number here that is to be written in place of true positive. Okay. Now similarly, this false positive means that you predicted it to be positive. Okay. So what does this mean is that your model is falsely predicting it to be positive. That is, you predicted it to be positive, but actually it was negative. So if you look at the previous example where you had 1000 points belonging to class 1 and 100 points belonging to class 2 and you predicted everything to be belonging to class 1, then what is your true positive value? True positive is 1000, because you predicted 1000 points to be of class 1 and actually 1000 points are of class 1. So the true positive value is 1000 And what is false positive? So there were 100 points which were actually not positive, but you predicted them to be positive. Okay. Then the false positive is given to be 100. Now, if you see, in accuracy, we had single value, right? But in case of your confusion matrix, these positions, this false positive and this false negative, gives you extra measure whether your performance, whether your model is performing good or not. So if you have some value at some large value at false positive and false negative, that means your model might not be doing very well. Okay. Now this position, this is false negative. What does this mean? That your actual data had positive labels, but your model has predicted it to be negative. So this is just the opposite of false positive. What is true negative? That your data was negative and you also predicted it to be negative. So whatever you have on the diagonal position, if that value is large, that would indicate that your model is doing good. But whatever is on your other diagonal, if that value is large, that would mean that your model is not doing that great. Okay. So this is the crux of confusion matrix. I think I should have an example too. Yeah. So we will try to solve an example. So this is a very small data set consisting of 10 points, right? And you have, I should have hidden this result thing. Okay. So now, if we look at the that kind of data set, we have 10 data points, right? And we have two classes. One is dog, another is not dog. So if being dog is positive class and being not dog is let's say negative class, then we have to find the confusion matrix for this particular example. Okay. Now if you look at the first example, that actual data was dog and we predicted it to be dog, then what kind of data set it is? This is actually true positive, right? Yeah, so this is true positive. Now if we look at our second example, this says that data point was actually dog, but it was predicted to be not dog. So it was actually positive but predicted to be negative. So this is false negative because it has been predicted falsely negative. So let's verify. Yeah, this is false negative. Again, dog would be true positive. It was not dog and it was predicted not dog. So this is true negative, right? Again, true positive. Now this example has that it was actually not dog, but it was falsely predicted to be dog. That is, it was falsely predicted to be positive. So this is false positive, right? Again, dog is true positive, dog is true positive, not dog, true negative, not dog, true negative. Okay. Now, if you have to write the confusion matrix corresponding to this, then we will count. So it will have 4 positions, right? So for the first position, we will count the number of true positives. So this is 1, 2, 3, 4, 5. So the first position will have 5 values over here, right? What is the second position? Second position was false positive, right? So the second position will have only 1 value, right? So it will be 1. So now comes the value, this is false negative, this position. So this is false negative, this is also 1, and true negative is 3. Okay. So this is how you create your confusion matrices. And if you look at, creating the confusion matrix is not that kind of a task, but to know what this confusion matrix is conveying is important. So if you look at this confusion matrix, so because these diagonal entries are high, right, when compared to the this semi-diagonal or the other diagonal thing, so this model is sort of doing well, right? This is sort of performing good. Okay, because these values are quite low and these values are high. Okay. So yeah, somebody is joining. That person. Right. Okay. Okay. Now, so in the lecture, professor talked about binary class classification whenever he talked about okay, so if you want to calculate the accuracy would be so number of correctly classified point, that is true positive plus uh, true negative, that is 5 plus 3 8, divided by total number of points, that is 10. So the accuracy will be 0.8, or if you want to write it in terms of percentage, it will be 80%. So whoever has written is correct. So the accuracy for this model is 80%. Okay. So yeah, so in the lecture, professor focused more on binary class classification. Although binary class classifications are very important, but in real life, at many places, you also encounter multi-class classification, where your data points has more than two label. Okay. So for multi-class classification, there are two things that you can write. Okay. When you talk about confusion matrix, so one is that, let's say this is class 1, this is class 2, this is class 3. Similarly, here this is class 1, class 2, class 3. So what does this position mean? This particular thing, this positions mean that it was actually class 1, okay, because it is coming from the column of actual C1, and it was also predicted to be of C1. Okay, so this is what this position means. Okay, so similarly, if you look at some other random position, okay, so if you, let's say you look at this position, this red portion, which I'm sort of also highlighting by green. Okay, so what does this position mean? This position means that your point was actually from class C3, but your model predicted it to be C2. So how many such points would be there? You will write it over there in this particular position. Okay, so this way you can find a confusion matrix for your multi-class classification. Okay, also one more thing. So this kind of matrix you can write to visualize that whether your model is performing great or not. So if your diagonal entries are high compared to the other entries, then it is sort of performing good. But one more interpretation for this is, what you can do is, so if you remember, how do we learn for multi-class setup? One method was 1 versus rest. Okay, so this was 1 versus rest. So for every class, you can create a separate confusion matrix on the similar lines of 1 versus rest. So what you can do is, you can treat your class C1 as positive and the rest everything as negative. Okay, so how would that matrix look like? So then, if you just compare it to this particular matrix, its first position will be same as this matrix, right? This value, let's say this is V1, this will be same, right? What will be here? Here you will have, let's say this is V2, this is V3, then you will have V2 plus V3, which is your false positive. Okay. And similarly, here you will have false negative being, let's say this is VW2, Z2. So this would be W2 plus Z2. Okay. And you can sum up these three things over here. Sorry, these two things over here. So you can create a separate confusion matrix for every class 2. That also gives you a lot of insight about your model's performance, right? Okay. So any doubt till this point about this confusion matrix? Then we will move to precision and recall. Okay. So here is a question sort of very similar to what is mentioned in your assignment. So there are 165 patients who are being tested for some disease. So you have to predict presence or absence using a binary classification, and you obtain following confusion matrix. Okay. So you are asked the total number of actual positive samples. Okay. So you are being asked total number of actual positive samples. So total number of actual positive samples. Okay. So what is total number of actual positive samples? That would mean that the samples which samples, okay, so let me use some abbreviation, which were actually positive and were predicted to be positive, okay, plus samples which were actually positive but predicted to be negative. Okay, so what does this mean? This is true positive and this is false negative, right? So yeah, so you will sum up this particular row. So this is 90 plus 15, which is 105. Okay. So you have a similar question in your assignment. You can calculate that too. And so here you see that when I use my notation, in my notation, I wrote this position to be false positive, but here they are using this position as false negative. So you can stick to either one of those notation. That is fine. Okay. So the sum of first row gave you the total number of actual positive points. What would be the sum of second row? Second row would give you the sum of actual negative points, okay, or the negative samples. What would be the sum of first column? First column would give you the total number of samples that were predicted to be positive. Okay, not the actual number of positive points, but total number of points that were predicted to be positive. And similarly, this would give you the total number of points that were predicted to be negative. Okay. Any doubt? Okay. So now we talked about accuracy, and with the help of an example, we saw that accuracy is not always good because we had an example where we had 90% accuracy, but the model was pretty bad because it was predicting everything belonging to class 1. Okay. So we have other measure of classification. So the first one is something that is called as precision. So what does yeah, somebody has something to ask. Okay. So what does precision mean? So precision mean, so among the predictions that you are making, that you are calling to be positive class, how precise your predictions are. So that means out of the positively predicted class, how many of them are actually of positive class. Okay, so which is true positive divided by total number of points that were predicted to be positive. Okay. Now another notion that you have is of recall. Okay, so recalls mean out of total actual positive samples, so remember this word, actual positive samples, how many samples were you able to recall? Okay, so how many samples were you able to retrieve to be positive? So how many you were able to retrieve is true positive divided by total number of actual positive class. Okay, so the formula is given by true positive divided by true positive plus false negative. Okay, these are straight away simple formulas and you can use them to calculate precision and recall. Now these are two sort of measures. We want to combine them. So to combine them, we take their harmonic mean and we obtain the formula of F1 score, which is given by 2 times of precision into recall divided by precision plus recall. Okay. So somebody was joining. Let me admit that person. Okay. Great. Okay. So this is what is meant by F1 score. So we have an example here, and we want to calculate all these three things, that is precision, recall, as well as the F1 score. Okay. And we have all the values available with us. You raise your hand. You have something to say.
Sir, please explain again what rows, addition of rows and columns of rows mean.
Okay. So rather than remembering what addition of rows and columns mean, what you can see is, I'll explain here only. So
Okay.
in this particular example, what is written in this row? The row is sum of true positive plus false positive.
Hmm.
Okay. So what does this mean is true positive. What is the meaning of true positive? Meaning is that you are actually of positive class and you are being predicted of positive class, right?
Okay. Yes, sir.
And what does this mean? That you are actually not of positive class, you are of negative class, but you are being predicted as positive class. So what would their sum mean? Their sum would mean that total number of samples which were predicted to be of positive class.
Positive. Okay.
Similarly, for the second row, you can find. Okay. So when you add uh, true positive with false positive or true negative with false negative, you get total number of samples uh, predicted of being of a particular class, right?
Yes,
So
sir.
the other part is, so what is the sum of a column? Sum of a column would mean that you are summing up a number of true positives plus false negative. So false negative means that actually it was of positive class, right? But it is predicted negative. So the sum would mean the total number of samples which were of actually of positive class. Okay. Okay. Was I clear?
Yes, sir.
Okay. Thank you. Okay. Can you mute yourself? Thank you. Okay, so now we have to calculate the precision, recall, and the F1 score. So what was the formula for precision? If we go above, the precision was true positive divided by true positive plus false positive. So what is true positive? True positive is 560 divided by 560 plus false positive is 60. So this is 560 by 620. What is the value? Can someone just calculate and tell me? Okay, so I'm believing you that this must be correct. So this is 0.903. And what is my recall? Recall is true positive divided by true positive plus false negative. Yeah. So this is 560 divided by 560 plus 50, which you are saying is 0.918. Okay. So this is how we calculate precision and recall. The next thing that is left is your F1 score. F1 score is 2 times of precision into recall divided by precision plus recall. Can someone again calculate this for me? You can use the calculator. That's fine. Into 2 divided by 0.903 plus 0.918. Can you please calculate? I don't think you would get 10. Yeah, 10 won't be possible. This is 0.9, right? And this is 0.918. We have two different answers. Can the third person check and tell me what they are getting? This is just simple calculation that you have to do on a calculator. So I did it on calculator and I'm also getting 0.910. So my 0.910 is the F1 score for this particular model. Yeah. Okay. So this is how you calculate your F1 score, precision and recall. So you have a question in assignment, you can tackle it the same way, right? Now, this was for binary class, right? Now what about multi-class? How do we calculate our precision or recall or our F1 score? So what we generally do is we calculate F1 score for every class individually, and then we take average of these class. But how we take average? Based on that, we have some variants of F1 score known as macro F1 score and micro F1 score, and you can have a third variant called as weighted F1 score. So you calculate F1 score separately for each class, and then you sort of average them or take a weighted average in a special way to obtain some unique values. Okay. So what about so here I have taken this example from a website called iamirsood.com. So you have three classes. First is aeroplane, second is boat, third is car, and this along every row you have this predicted thing, and along here you have the actual label. So again, this is just notation he has sort of flipped to what we were using. So if you want to write this thing as a true positive, true and false positive and false negative sort of thing. So for aeroplane, you have 2 points that were actually aeroplane and were predicted to be aeroplane, right? So for aeroplane, your true positive value is 2, right? Now, for aeroplane, what is your false positive? So things that were being predicted as aeroplane, right, but were actually not aeroplane. So this would be sum of these two quantities, right? So they are being predicted as positive, but they're actually not aeroplanes. So what is the value of this thing? So this is false positive is 1, right? So your false positive is 1. And again, the other thing is false negative. So you are actually aeroplane, but you are being predicted something else. Okay. So this is false negative, which is again 1. So they have compiled it and written it as 1. Okay. So similarly for both, they have done that their true positive is 1, false positive is 3. This is sum of this value plus this value, which is 3. Okay. And similarly for car, they have calculated these values for us. Okay. Now, based on these values, we will try to calculate the sort of the F1 score for these things, right? So to simplify for the time being the calculation, okay, we can try calculating the precision recall because the calculation is quite simple here. So what is precision? Precision, and let's calculate recall also, and we have some values to confirm also whether we are doing correct or not. Okay, so precision would be 2 divided by 2 plus 1, right? This is 2 by 3. Somebody has joined, admit. Okay, and what is recall? Recall is again 2 by 3. In this case, precision is 1 by 4. Recall is 1, which is quite good. And here the precision is 1. and the recall is 3 upon 3 plus 3, this is half, right? So I think this is what they should have got. Yeah. So this is 2 by 3, 2 by 3, 0.251 and 1 and 0.5, right? So if you calculate the F1 score, this is something you get for every class, right? So for aeroplane, you got this as your F1 score. For boat, you got this as your F1 score. For car, you got this value as your F1 score. Now, I'll discuss three methods to average these F1 score. First one is called as macro F1 score. So what is macro F1 score? This is the most intuitive one. So in macro F1 score, you take the average of F1 score of every F1 score. So macro F1 score would be nothing but 0.67 plus 0.4 plus 0.67 divided by 3. So this is what you will obtain as your macro F1 score. So this would be something about, so this is 4, 7 for 11, 6, 17, and this would be so this is 5, 8, I guess, right? I think I'm correct. Yeah. So this is something that you obtain as your macro F1 score. Okay. Now, based on your application, you might want that predicting car is more important to you than predicting whether it's boat or aeroplane. For example, let's say somebody created a testing technique which tests for COVID-19 as well as, let's say, some other respiratory disease, for example, tuberculosis. I'm not sure whether there can be a method which tests these two at the same time. But when there is a spread of COVID-19 virus, then testing COVID-19 virus gains more importance, right? So performing well on testing a COVID virus is of more importance as compared to testing for tuberculosis for some certain time period. Okay. So in similar way, let's assume there is a situation when checking whether something is car or not is more important to you as compared to the other two. Then what you can do is you can give this F1 score of car more weight. Let's say what you do, you give 0.6 weight to your car, okay, and you give a 0.2 score to your other two, okay. So this way you obtain something that is called as weighted F1 score, and this weights will depend totally on your application, so where you are using it, okay. So yeah, the other thing that is common is known as micro F1 score. So earlier we had macro F1 score, now we have micro F1 score. Here what we do is, so rather than calculating the F1 score individually, what we can do is we count total number of true positive and total number of true negative and total number of false positive and false negative throughout the data. So overall in the data, we calculate these values, and based on the overall values, we calculate the precision recall and then the F1 score. Okay. For example, in this case, what is the total number of true positive values? So this is 6. What is total number of false positive? This is 4 and 4. So what would be the precision for this thing? So precision would be 6 divided by 10, right? So this is 0.6. What would be recall? Recall again would be 0.6, right? So what is my F1 score? Micro F1 score, sorry. So micro F1 score is 2 into 0.6 into 0.6 divided by 0.6 plus 0.6, and this is nothing but 0.6, right? So this is 2 into 0.6, you will cancel that out and you will get 0.6. So there I talked about three variants of F1 score: macro F1 score, weighted F1 score, and micro F1 score. Okay. So just few passing comments. So if you have only two classes, or that is you have some binary data set, then your micro F1 is equivalent to your accuracy. In case you have only two classes, okay, because you are counting the total number of this true positive and false positive and everything. So this is same, right? And when you have imbalanced data set, let's say for the example we considered where class 1 had 1000 data points and class 2 had only 100 data points. In those kind of situations, you will go for macro F1 score, and this is a better measure to preserve your imbalanced data set. Okay. So these were the two passing comments that I wanted to make. Any doubt in classification metrics at like whatever we discussed till now? How do we test the performance of a model? Then we will move to this Gram-Schmidt's process, and yeah. So I'll wait for 2-3 minutes till 6:50 for any doubts on this classification metric. Anybody has any doubt or any other doubts related to classification as in whole? Because now whatever topics we would be covering would be more mathematical, and I am not sure whether we would get back to this classification things towards the last of the course. So any doubts related to classification or anything, you can ask, even if from machine learning perspective or any other perspective, you are free to ask.
Sir, can you scroll to above example?
Sure, sure. Do you want me to scroll more, or this much is fine for you?
This is fine.
Okay. Okay. So if nobody has anything to ask, then I'll go to something known as Gram-Schmidt's orthogonalization process. Okay. So orthogonalization is the important word here. So just a very small recap. I am sure everybody of you know what is orthogonal vectors and what is orthonormal vector. So we call set V1, V2, Vn to be, somebody is joining, to be orthogonal, right? Orthogonal if Vi dot product with Vj is 0 for all I and j, right? Except like whenever I is not equal to j, right? If your I is equal to j, then it should not be equal to 0. And this is something what is known as orthogonal, that your vectors are sort of perpendicular to each other, right? And what is orthonormal? Orthonormal is that when your set is orthogonal plus every vector has length 1, right? That is, what does length 1 means? That Vi transpose with itself is 1 for all I, right? So this is what is meant by orthogonal and orthonormal. Okay. Now, what is this Gram-Schmidt's process? This is a very common process. What it is used for? It is used to convert your basis vectors into an orthogonal basis set, right? So if you have some given set of linearly independent vectors, you want to convert it into a set of orthogonal vectors, as orthogonal vectors are also linearly independent. So you can use this method to convert your set of vectors to orthogonal vectors. Okay. So I'll just motivate this a bit. Okay. Let's say, why do we want to convert our vectors to orthogonal sets, right? What is the need, right? So you might remember either from linear algebra or whatever we did in this course, many a times if you have, let's say, a basis equal to beta 1, beta 2 and so on, you want to write any arbitrary vector in terms of alpha times beta 1 plus alpha 2 beta 2, like you want to represent any vector as a sum of your basis vectors. So you have to calculate these alpha 1, alpha 2 and so on, right? But if you have let's say orthogonal basis vector, or you have linearly independent orthogonal set, if you want to write your vector v in terms of these things, then you can easily calculate your alpha 1s and alpha 2s. Okay, so what would be those alpha 1 and alpha 2? That would be nothing but, let's say you want to represent v in terms of beta 1, beta 2, then your alpha 1 would be dot product of v with beta 1 divided by norm of beta 1 square, right? This is your alpha 1. Okay, and similarly you can find all the alphas straight away without solving any system of linear equations or anything. Okay, so this is what is written in this theorem. Let's say you have v1, v2, vn, okay, as an orthogonal subset of v. Because this is orthogonal, this is automatically linearly independent, and you want to write y in terms of this alpha 1 v1 plus alpha 2 v2 and so on, then this can be done in this way. Okay, yeah, somebody has something to say.
Can you explain this one more time, sir?
Okay, sure.
That VD into BY, B1 divided by mode of B1 square, sir? That part?
Okay.
Okay. How we are finding that alpha 1, sir?
Okay.
Alpha 1 is scalar, no, sir?
That is a scalar, right?
Okay.
So if you have this V inner product with beta 1, so this is a symbol for inner product, right? So this would mean a scalar value, right? And again, the denominator is also in scalar. So if the confusion was regarding whether it will be a scalar, then it is still, it is a scalar. Now I'll explain it again. So what I was saying was, I was sort of motivating why do we want an orthogonal basis for our vector space or any application, right? So what I was saying was that when we have an orthogonal basis, let's say your basis is beta 1, beta 2 and beta n, and this is orthogonal, then without solving this system of equation, you can straight away find your alpha 1 using your formula. Let's say you are writing v in terms of these things. So v with dot product with beta 1 divided by beta 1 norm. So this is the straight away formula that you can use. Now am I clear? Now,
Okay,
why do we do that? I'll come to this. Okay, so this picture would explain a lot. Okay, so even before this picture, let's say I have this shape. Yeah, let's say this is your 2D plane that we have been all working with since our childhood. So yeah, so this is a normal 2D plane that we all have been working since our childhood. Let's say you have some vector. Yeah, you have this vector, right? And you want to write it in terms of your E1 and E2. That is your standard basis, right? So what you do is, let's say this is some random number. Let's say this is x comma y. Then you write it. How do you write it? You write it x times E1 dot y times E2, right? Why do you do that? Actually, if you look at it, so what you do is you take a projection of this point on your x-axis. Okay, you take the projection of this point on your x-axis, and this length that you will obtain is x. I'll thicken this up a little bit. So this length that you obtain is your x, right? That's why you are writing this x into E1, and your E was sort of already a normal vector because this is 1, 0. Otherwise, you would have normalized it, right? So this is just the projection of this point that you are taking on x-axis, and similarly on the y-axis that you are taking, you are writing that as its coefficient. So because this E1 and E2 were sort of orthogonal, somebody is speaking something. You can speak. Rohini, you had something to ask?
No, sir.
Okay, so because your E1 and E2 were orthogonal and unit vector, you were able to write it very cleanly, right? So whenever you have sort of orthogonal vectors, what you can do is you can take the projection of your vector onto a orthogonal vector, and that would be your coefficient. Okay, so for example, let's say rather than this thing, if you had some other orthogonal set, then alpha 1, whatever formula I wrote, if you just split this a bit, so this is v dot beta 1, beta 1 norm into beta 1 norm. If you just look at this portion, right, ignore the other part, this is nothing but the projection of your vector v onto the vector beta 1. Okay, and this other beta 1 just comes into picture because you want to normalize your this vector in which you are representing. Okay, so this is what this theorem is saying, that if you have, let's say, some v1, v2, vk as orthogonal set, then you can write y in this form, that is your y inner product with v1 or v2, whichever one you are working with, and divided by your v1 square into your vector vi. This vi would give you the direction, right? So you
Yes,
sum
sir.
them up to obtain
Okay.
that. Yeah.
Okay.
Yeah. Okay. So I think most of you would know how to calculate the projection. Okay. But still, I'll just for somebody who don't know, let's say you have a vector A, right? And you want to find its projection onto B. Okay. Now, if you recall your formula for A dot B, this is nothing but AB cos theta, right? So this is your angle theta, and if you use simple trigonometry over here, because this is 90-degree, when you're taking the projection, this is A cos theta. Okay. So what is the value of A cos theta that you can obtain from here? You'll just send this thing this side. So this is A dot B divided by norm B. Okay. And if you want to write this vector from here to here, okay, then what it is? So this would be again, so the value of length of this vector is this much. And what is the angle of that vector? The angle would, the direction would be in the direction of B divided by norm B. Because we want to take the unit direction in terms of, because we have already considered the length over here. So when we are talking about direction, we want to consider only the unit vector in that direction. So this is how these people have derived, that they are taking the projection along every orthogonal vector, and then they are just summing it up. Okay. So this is the idea behind using orthogonal basis set. Okay. And yeah. So we will continue with our Gram-Schmidt orthogonalization process, right? So this is not a theorem, but a process on how to convert your set to a orthogonal set. Okay. So just to decode this theorem for you, so you are given with something called W1, W2, Wn. You are given with this. Okay. And you want to convert it to orthogonal set V1 to Vn. Okay. How do you obtain this set? So I'll just rather than going into this peculiarity, I'll just write it down. So for the first v1, you straight away assign the first vector w1. For the first thing, you don't do anything. Okay. For the second one, what you do is, so you take the projection of your w2 vector. Okay. You take the projection of your w2 vector in direction of v1. Okay. Oh, I should avoid this thing. Yeah. In the direction of v1. Okay. So what is this? This is the projection of w2 in direction of v1. Now what we actually want is that my v1 and v2 should be perpendicular to each other, right? Now what we do is, so let's say this is your v1 and this is your v2. Now you want them to be perpendicular to each other. So what you do is, you take this projection, okay, and you subtract this projection from the original vector. So subtracting would mean that you don't have anything left in this vector that is inclined with the angle of this particular vector, the second vector, right? So if you subtract this projection from your w2, whatever is left with you is actually orthogonal to your v1. Okay, so this value that you get, yeah.
So can you please explain it again?
Okay, so sure, I'll explain it. So what did you did initially? For the first vector, you choose your first vector from existing list, right? Now for constructing the second vector, what you want is that your v2 should be perpendicular to v1. Okay, now how do we make a vector that is perpendicular to v1? So what we do is, from our w2, we subtract whatever quantity of v2 is inclined in direction of v1. So what we do is, we take the projection of your w2 in the direction of v1 and we subtract it from w2. So now this new vector that we have obtained is perpendicular to v1. Why? Because whatever component was parallel to your v1 or was inclined with v1, we have already subtracted that from v2. We have removed that from w2. Okay, so that's why whatever is left is perpendicular now to v1. Now am I clear? Whoever asked me to repeat. If I'm not, please let me know. I'll try to explain it again. Was I clear?
Sir, projection part is the projection part. प्रोजेक्शन पार्ट से सर हमारा वो होता है ना, जो हमारा अगर हम एक्स एक्सिस के अलॉन्ग प्रोजेक्शन ले रहे हैं तो वो एक्स एक्सिस के पैरेलल होगी ना, तो इंक्लाइन पार्ट कैसे हुआ है?
हाँ देखो, अगर मान लो ये तुम्हारा एक्स एक्सिस है, ठीक है, ये वाई एक्सिस है, मान लो ये पॉइंट तुम्हारा कोई 3,5 है, ठीक है। अब मान लो इसका प्रोजेक्शन एक्स एक्सिस पे लोगे तो कितना आएगा? 3,0। वेक्टर के फॉर्म में लिख रहे हैं अभी हम, ये जो प्रोजेक्शन लेने के बाद वेक्टर आया ना वो लिख रहे हैं, 3,0 हुआ, ठीक है। अब अगर हम ओरिजिनल वाले में से 3,5 में से 3,0 हटा दें तो क्या बचेगा हमारे पास? 0,5। तो जो चीज हमारे पैरेलल आई एक्स एक्सिस से उसको हमने इसमें से हटा दिया, तो जो बचा हमारे पास वो क्या रहा? whatever is left is 0,5, which is if you now see, तो ये जो ओरिजिनल वाला एक्स एक्सिस था और जो सब्ट्रैक्ट करने के बाद आया, these two are perpendicular to each other, right? तो वही हम यहाँ पे कर रहे हैं कि हमारे, हाँ बोलो,
तो क्लियर
हो गया ना? ठीक है, तो जो ये हमारा बीच वाला वेक्टर था जो यहाँ पे है, दिस इज आर W2। ओके, जो ये x एक्सिस था वो हमारा W1 है, और अब हमें फाइंड करना है y एक्सिस को, हमें y एक्सिस की तरफ जाना है। तो वॉट एवर विल ऑब्टेन थ्रू V2 इज आर y एक्सिस, if you compare this to this example. Okay, now what you will do for the third vector? For third vector, what you will do is from W3, now first you will subtract whatever you have in W3 parallel to V1. Okay, and then you'll also subtract whatever you have in W3 parallel to V2. Okay, तो जब दोनों को subtract कर देंगे we will get something which is perpendicular to both V1 as well as V2. So we will proceed in similar fashion, or if you want to generalize this thing for any Vk, then what you will get is from Wk you are subtracting its projection from every of the previous Vi's. So Vi from 1 to k minus 1. Okay. So this process is something that is known as Gram-Schmidt's orthogonalization process. So yeah.
सर वो
हाँ बोलो.
सर अगर हम 3,5 से आगे एक पॉइंट ले 6,8,
ठीक है,
तो हमने थर्ड V3 के केस में अगर हमने 3 पहले माइनस कर दिया है तो हम अगले
हाँ.
केस में 6 को माइनस करेंगे, हम फिर 3 माइनस करेंगे ना नेक्स्ट.
एक मिनट, हमने एक और वेक्टर ले लिया 6,8. ठीक है, अब क्या करना है?
सर तो जैसे कि थर्ड केस में हमने V3 की प्रोजेक्शन 1 के अलोंग माइनस करी, फिर हमने V2 के अलोंग माइनस करी, लेकिन V1 वाली तो पहली सब्ट्रैक्ट हो चुकी ना, दोबारा नहीं माइनस हो जाएगी.
नहीं, अब हम लोग सब्ट्रैक्ट किसमें से करेंगे? 6,8 में से करेंगे ना. तो 6,8 में से अगर हम लोग इसका प्रोजेक्शन लें तो कितना आएगा? 6. तो अब हमने सब्ट्रैक्ट किया तो कितना आया? 0,8 बचेगा, मतलब हमारे पास जो बचेगा वो 0,8 होगा. रुको, इसको 3D में समझते हैं. तुमने जो एग्जांपल लिया ना उसको एक 3D में समझते हैं, फिगर के थ्रू ही समझ जाएगा. मान लो हमारे पास अब x y z 3 एक्सिस हैं, ठीक है, और स्टार्टिंग में हमने शुरू किया v1 जो है हमारा 1,0,0 से शुरू किया मान लो. ठीक है, एनीबडी हियर हु इज नॉट कंफर्टेबल विद हिंदी, इफ देयर इज समवन प्लीज रेज योर हैंड्स, अदर आई टू एक्सप्लेन दिस पोर्शन आई विल स्विच टू हिंदी, राइट? So if there is anybody who don't understand English, please let me know. ठीक है, तो अब मान लो कि हमारा जो पहला वेक्टर है वो 1,0,0 है. ठीक है, दूसरा वेक्टर जो है हमारा, तुम सेम ही लेते हैं, ये 3, 5 और कुछ रैंडम वैल्यू ले लेते हैं, 2 ले लेते हैं, और थर्ड वाले को क्या लेते हैं? 6, 8, 4 ले लेते हैं. ठीक है, अब देखो 1,0,0 पहला वाला था, पहले वाले को हमने 1,0,0 ही छोड़ दिया. ठीक है, दूसरा वेक्टर हमारा कुछ 3, 5, 2 आएगा. ठीक है, अब हमें क्या करना है? अगर हम 3, 5, 2 का प्रोजेक्शन x एक्सिस पे लेंगे तो x एक्सिस पे प्रोजेक्शन क्या आएगा? 3,0,0 है ना. अब जब हमने उसको v2 में से माइनस किया तो हमारे पास बचा 0,5,2. ठीक, पर हम लोग क्या करेंगे इसको? हाँ, 0,5,2. ठीक है, अब ये अगर तुम देखोगे, ये वैसे तो एक वेक्टर दिख रहा है कि 0,5,2, पर ये कैसा रहेगा? x नहीं रहेगा इसमें और yz प्लेन जैसा बन जाएगा. ठीक है, अभी इतना ध्यान दो. अब हम लोग क्या करेंगे कि ये v2 बन गया हमारा. ठीक है, अब अगर v2 और v1 को देखोगे तो दोनों का डॉट प्रोडक्ट क्या है? 0 आ रहा है. तो ये श्योर है कि हमारा v1 और v2 जो अभी बना है वो ऑर्थोगोनल बन गया है. ठीक है, अब हम लोगों को क्या बनाना है? अब हम लोगों को बनाना है v3. तो v3 में से हम लोग v2 भी सब्ट्रैक्ट करेंगे. तो v2 के अलोंग इसका प्रोजेक्शन क्या आएगा? तो इसका आएगा, तो हम लोग v3 बनाने के लिए क्या क्या करेंगे? सॉरी, ये w3 बनाने के लिए क्या क्या करेंगे? इसको w2 नाम देते हैं. ठीक है, v2 में से क्या क्या सब्ट्रैक्ट करेंगे हम लोग? 6, 8, 4 है. इसमें से पहले इसका प्रोजेक्शन अलोंग, अगर हम लोग मान लो v2 लेते हैं, सॉरी v1 लेते हैं, तो क्या होगा? 6,0,0. अब क्या करना है हमें कि इसका प्रोजेक्शन अलोंग थर्ड वाला भी लेना है. अगर हम लोग बस इतना कर दें, ठीक है, इफ वी डू जस्ट दिस मच, तो क्या होगा कि ये जो W3 है वो V1 से तो परपेंडिकुलर हो जाएगा, बट इट वोंट बी परपेंडिकुलर टू V2, राइट? और अगर हम लोग ये वाला टर्म ना रिमूव करें इसमें से 6,0,0, तो ये V3 के बस V3 के उससे वो कर दें कि वी विल सबट्रैक्ट जस्ट इट्स प्रोजेक्शन, दिस इज W3, सॉरी V3 ट्रांसपोज V2 डिवाइडेड बाय V2 नॉर्म. अगर बस ये चीज कर दें हम लोग, सो इट वोंट बी परपेंडिकुलर टू V2, क्योंकि ये जो डायरेक्शन है, मान लो जो 0,5,2 था, इसमें कोई भी कंपोनेंट हमारा V1 के पैरेलल है ही नहीं. So everything that we have left over here, we don't have anything that is parallel to V1. तो अगर हम लोग YZ एक्सिस पे प्रोजेक्शन लेके माइनस करते हैं, अगर कुछ भी प्रोजेक्शन इस पे लेंगे, so that will be always of form 0, x, y. तो हम लोग इसमें से कुछ भी अगर माइनस करेंगे तो इन्हीं दोनों पोजीशन से माइनस होगा. ठीक है, फर्स्ट वाले पोजीशन से हमारा कुछ माइनस ही नहीं होगा. सो वी वोंट बी एबल टू मेक इट पैरेलल टू V2. एक एग्जांपल करते हैं इसके बाद. ये एग्जांपल थोड़ा सा वैसा हो जाएगा कैलकुलेशन वाइज. वी हैव अ मच सिंपलर एग्जांपल, वो देख के समझ जाएगा. इफ यू डोंट गेट इट, just ask me again. Okay, we'll just do this example. So here we are given with three vectors. बस ये एग्जांपल तक वेट कर लो. आई एम श्योर यू विल अंडरस्टैंड दिस पार्ट. So here we are given with W1, W2 and W3. Okay, and we have been asked to convert it to orthogonalized set, and later we have been also asked to normalize these vectors. That we will do later on. Okay, so what did I say? That for the first vector we will just pick the first from the existing list, right? So this would be 1 0 1 0, right? For the second one, what we need to do is we need to subtract the projection of W2 onto W1, right, into V1. ठीक है, तो अभी ये नॉर्म कैलकुलेट करना पड़ेगा V1 का. तो V1 का नॉर्म हो जाएगा स्क्वायर रूट ऑफ 1 प्लस 1, और उसका स्क्वायर क्या हो जाएगा 2. ठीक है, तो अब अगर इसको हम लोग वैसे फॉर्म में लिखें, दिस वुड बी 1 1 1 1 minus the top, so the denominator is 2 here. So what is the top part? W2 dot product with V1. So W2 is this and V1 is this, so its dot product is 1 plus 0, right? So this is 1 plus 0, again plus 1, this is 2, and plus 0. So this is the dot product is 2, right? So ये 2 हो गया, and this is your 1 0 0, sorry, this is 1 0 1 0. So you are left with 0 1 0 1. ठीक है, तो अभी देखो जो V1 था हमारा वो था 1 0 1 0, उसमें से हमने पैरेलल वाला कंपोनेंट रिमूव कर दिया. तो V2 दैट वी ऑब्टेन्ड इज 0 1 0 1. अगर देखेंगे तो ये दोनों क्या है, परपेंडिकुलर है. यू टेक द डॉट प्रोडक्ट, 0 आएगा. ठीक है, अब जब हम लोग V3 निकाल रहे हैं, आई विल कम टू योर पॉइंट. ओके, अब what is my V3? V3 is W3. Now what you are saying is that we have already subtracted this particular component. Why do we need to subtract it from here as well, right? अब क्यों करना है? क्योंकि अगर हम लोग मान लो बस W2 वाला कंपोनेंट सब्ट्रैक्ट करें, let's say what we do is W3 V2 divided by V2 norm into V2, तो क्या मिलता है? This is not correct right now, but we are just checking कि अगर हम लोग ऐसा करें तो क्या होता है. ठीक है, तो this would be 0 1 2 1 minus again this V3 into W2 is, this is my V3 and this is my W2, right? डॉट प्रोडक्ट लें तो फर्स्ट कंपोनेंट 0 प्लस 1 फिर 0 प्लस 1, so this is again 2. इसका नॉर्म फिर से नॉर्म स्क्वायर 2 आएगा, and this is 0 1 0 1. क्या वैल्यू आई अपने पास? So the first component is 0 minus 0 is 0, 1 minus 1 is 0, 2 minus 0 is 2, right? And 1 minus 1 is 0. अब अगर हम लोग देखें इसको, right, तो V3 और W2 का जो डॉट प्रोडक्ट है, ठीक है, V3 और V2 का, ये दोनों 0 होगा. ठीक है, पर अगर तुम देखो V1 का डॉट प्रोडक्ट V3 के साथ अगर निकालोगे, देन यू विल गेट 2. थर्ड कंपोनेंट पे यहाँ भी 1 है, थर्ड कंपोनेंट पे यहाँ 2 है, यू विल गेट 2. व्हाई डिड दिस थिंग हैपन? बिकॉज हम लोगों ने W2 के पैरेलल जो भी कंपोनेंट था V3 का वो रिमूव कर दिया. पर जब वो रिमूव कर रहे हैं, क्योंकि W2 में W1 का कुछ भी बचा ही नहीं है, तो वी आर नॉट रिमूविंग एनीथिंग फ्रॉम W1 विच इज, सो एनीथिंग विच इज पैरेलल टू W1 वो हम लोग रिमूव नहीं कर पा रहे हैं। इसलिए हम लोग इधर एक एक्स्ट्रा कंपोनेंट ऐड होगा जिसमें W1 के भी जो पैरेलल चीजें हैं वो भी रिमूव होगी। नाउ एम आई क्लियर whoever asked this question?
Yes, sir.
ओके, तो अब हम लोग इसको कैलकुलेट करते हैं सही से कि व्हाट वुड बी W3। ठीक है, तो V3 क्या होगा अब हमारा? V3 वुड बी दिस इज 0 1 2 1 माइनस W3 का डॉट प्रोडक्ट विद W1 divided by W1 norm W1, and the rest part we just calculated. This was minus 1 times V2, right? We just calculated it, that's why I'm not writing it. Its formula is W3 comma V2 divided by V2 square V2, right? So yeah, so this is nothing but 0 1 2 1 minus V3 and V1. So V3 is this and V1 is this. So this would be 2 again, right? And again 2, right? It's a good example that everything is reducing to 2, right? So, and V1 is nothing but 1 0 1 0 0 minus 0 1 0 1. So what do we obtain? This is 0 minus 1 minus 0. This is minus 1, right? And this is 1 minus 0 minus 1. This is 0. 2 minus 1 minus 0 is 1. And this is 1 minus 0 minus 1 is 0. So V3 we obtain to be minus 1 0 1 0. Now if you take its dot product between these two, this is 0, right? And now even if you take its dot product with V1, because this position we got minus, then again it will be 0. Okay, so this is how we orthogonalize any basis that you have. Now the question also had a small part where they asked us to normalize these vectors too, right? So normalization is very easy. So how do we normalize it? So we just need to divide them by a norm. So what was the norm of V1? It was √2, right? So norm square was 2. So what was norm of V1? This was the square root of 2. So you can just obtain 1 by √2, 0, 1 by √2, 0. Similarly for V2, you can have 0, 1 by √2, 0, 1 by √2. And for V3, you can have minus 1 by √2, 0, 1 by √2, 0. Right. So, any doubt in this Gram-Schmidt process? Okay. So this polar decomposition, I'll just state the formula. I won't be solving a lot of problems because the example or the question that is asked in the assignment, if you just understand what this polar decomposition does, you would be able to solve that problem. So we'll then move to this Jordan canonical form and try to solve 2-3 problems over there. Okay. So what is this polar decomposition? So in polar decomposition, you decompose or write your matrix as product of two matrices. So if you have a matrix A, right, which is let's say M cross N, then you write it as a product of two matrices. First one is W, which is an orthogonal matrix. What does an orthogonal matrix mean? Orthogonal matrix is something whose every column is an orthonormal vector. Okay. So this is column. And the second matrix that you have is a positive semi-definite matrix. So for the positive semi-definite part, what is the property? That for any vector V, VP V transpose is always greater than or equal to 0. Okay, so this is the property of a positive semi-definite matrix. So the question is based on just these two properties of your orthogonal matrix and your positive semi-definite matrix. But I'll just include, if you have a matrix A, how do you calculate its polar decomposition? It's calculated. Okay, so let's say if you have a matrix A and you find its singular value decomposition, which is given by U dV transpose, then you can obtain your matrix W by U times V transpose. Okay, and you can obtain your matrix P by formula VD V transpose. So if you have to, if somebody tells you to find the polar decomposition, you first of all find its singular value decomposition, and then using the U, D and V transpose obtained, you can straight away find your polar decomposition. Okay, so I'll talk about polar decomposition only this much, and then we'll move to your this Jordan canonical form. Okay. Okay, so sort of some yeah. So when you were reading about this eigenvalue and eigenvector, so one motivation was that you can, so what you can do is, so if you have a matrix A, you can write it as form PDP inverse, right? And then let's say if you have to find a to the power 100, what you can do is, so this is PDP inverse repeated 100 times, right? So this would be nothing but P, this P inverse P would be identity. So this would be P d to the power 100 P inverse, and calculating d to the power 100 for a diagonal matrix is very easy, because let's say if you have a diagonal matrix like let's say this is 1 2 0 0, if you want to calculate its power 100, then you can just do 1 to the power 100 0 0 2 to the power 100. So we talked about this. So calculating these kind of complex things for matrix became easy. Another thing was that yeah, you can solve your system of linear equation quite easily. Okay, but not every matrix was diagonalizable, right? So when is a matrix diagonalizable? So whenever you find an eigenvalue, so eigenvalue, if you look at the characteristic polynomial, does have some multiplicity associated with it, which is called as your algebraic multiplicity. So if you are able to obtain those many number of independent eigenvectors, then your matrix is diagonalizable. If you are not able to obtain that, then what can we do, right? We want to use these kind of features, but our matrix is not diagonalizable, right? So what we do is, we, rather than using this D, we convert our matrix A, okay, into form S J S inverse, right, where J is a Jordan canonical form matrix. Okay, so in Jordan canonical form, your matrices have nice block structures. So you will have some blocks here, right? Everything rest is 0, and even in these blocks, only your diagonal and super diagonal entries are non-zero, and rest everything are 0 within these blocks also. Okay, so there is a lot of theory that if somebody is interested, he can study numerical linear algebra or an advanced level course in linear algebra, where you can find ways to easily calculate j to the power some high power. Okay, so there is a lot of theory around it. So what we want to do is, if we are not able to represent as some P diagonal matrix P inverse, at least we can do it something like S, some matrix which is close to diagonal, and some S inverse. Okay, so to do that, we go for Jordan canonical form. Okay, so yeah, so this is what it is. So we'll just talk about few things here before going to Jordan canonical form. First thing is known as characteristic polynomial. So what was the characteristic polynomial? We did it while doing eigenvalues and eigenvector. Let's say A is your matrix. Okay. So if you calculate, if you look at this equation, determinant of A minus lambda I is equal to 0. So this quantity, if you expand, you will get a polynomial. If you just ignore the equal to 0 part, right? If you calculate this, evaluate this, you will get a polynomial in lambda. So that particular polynomial is known as your characteristic polynomial, right? So what is a minimal polynomial? Minimal polynomial is nothing but the least degree monic polynomial, such that if you put your complete matrix A in that polynomial, you will get 0. Okay. For example, so there are 2-3 terms. Polynomial, you know what it is. Monic means that the leading degree. So let's say if it is a 5-degree polynomial, then the coefficient of your this highest power must be 1. That is what is meant by monic polynomial. And minimum degree is for any polynomial which is of lower degree than this polynomial. Your if you put the A in that polynomial, then you must not get equal to 0. Okay. So for example, if you look at, let's take some simple example. So let's say this is 4, 4, 0, 0. Then if you just look at this example, let's say 4 minus lambda. So yeah, so lambda minus 4, if you just look at this polynomial and you put your this matrix in this thing, then you will get 0, right? So this is the minimum polynomial for your matrix A. Okay. So this minimal polynomial and your characteristic polynomial will have some relation with Jordan canonical form that we will talk later on. Okay, that's why I just wanted to define it here. Now coming back to something that is related to your assignment. So this is the direct
Sir,
sum.
the-
Yeah.
The previous that won't be a null vector, a null matrix, no, sir. How
Which one?
that will be
Okay.
lambda minus 4i?
Yeah.
That is 6 is there, no, sir?
Yeah. So what I was saying.
4064. But
See,
4064, no, sir?
no, this is 0.
Okay.
Sorry.
Okay, sir. Okay.
Yeah. Okay. So let's get to this direct product. Okay. So if you have two matrix A and B, then the direct product is defined something like this, that you will write A as your top left block and B as your right bottom block, and rest everything will be 0. Okay. So if you have A and B, and you have calculated A direct sum with B, then how do you define characteristic polynomial for A direct sum B? That is simply characteristic polynomial of A multiplied by characteristic polynomial of B. So if you have, if you are given with characteristic polynomial of A and characteristic polynomial of B, then you just need to multiply them to obtain the characteristic polynomial of A direct sum B. Okay. Now for the minimal polynomial, the rule is that the minimal polynomial for A direct sum B is the LCM of minimum polynomial of A and minimum polynomial of B. For example, let's say minimal polynomial of A is, this is just an example, x minus 2, x minus 3 square, and x minus 4 to the power 5. Okay. And minimal polynomial for B is, let's say, x minus 1, x minus 3 to the power 4, and x minus 4 to the power 2. Then what is the minimal polynomial for A plus B? This is LCM of both of them. So x minus 2 is not in here. So x minus 2 will stay as it is. Now what is the, so if you look at x minus 3 to the power 2, x minus 3 to the power 4. So as you are taking LCM, so the power 4 will be retained. For the next part, this is x minus 4 to the power 5 will be retained. And at the last, x minus 1 you will get. So this is how you can find the minimal polynomial for direct sum. You just take the LCM of both these polynomials. Okay. Not the LCM of these parts, but the LCM of polynomials, right? That you should take care. Okay. Okay, yeah. So one more thing that I forgot to mention earlier was that this matrix S that you obtained. So if you had a diagonalizable matrix, right? So how did you obtain P? P consisted of, so the columns of P were the eigenvector for your matrix A, right? Now you don't have sufficient number of eigenvectors, so you use something that is called as generalized eigenvector. So we'll come to that. What is a generalized eigenvector? Okay. So yeah. Okay. So before this thing, I should introduce what is known as. Okay. So I'll just recall when you used to find eigenvalue and eigenvector for a matrix A. For A, so what you used to do is you used to first of all find determinant of A minus lambda I equal to 0. So this determinant of A minus lambda I equal to 0 used to give you some sort of equation whose left term used to be some polynomial, right? So for example, if you remember, you could have got something like this equal to 0. Okay. So what does this mean is that your lambda is equal to 2 is repeated 2 times. This is what we used to say then, that your set of eigenvalue is 2 comma 2 comma 3, right? So the number of times a particular eigenvalue is repeated, that is called as the arithmetic mean of that eigenvalue. So for 2, the arithmetic mean is 2. For 3, the arithmetic mean is 1. Okay. Now the next step you used to do is to find eigenvector corresponding to every eigenvalue. Okay. Now the number of independent eigenvectors corresponding to lambda is called its geometric mean. Okay. So just a simple thing that it is called as the geometric mean. So for this, if you had, let's say, 2 linearly independent eigenvectors you were able to find, then its geometric mean would be 2. Okay. Right. So after this, we have something that is called as Jordan block. Okay. So Jordan block of length k. So what is Jordan block of length k? So Jordan block will correspond always to one eigenvalue. Let's say this is lambda 0 and this will be of size k cross k. Okay. So if you have k here, then it is of size k cross k. On the diagonals, you will have that eigenvalue. So lambda 0 throughout. And on the super diagonal, you will have 1. And rest everything is 0. This is something that is known as Jordan block. So if you look at a Jordan block of length 2, for example, let's say this is Jordan block of length 2 with eigenvalue as 3. So this is 3, 3, right? On the super diagonal, you have 1 and 0 everywhere else. Let's say if you have Jordan block 3 of length of eigenvalue 2, so this is 2, 2, 2 on the diagonals, 1 and 1 on the super diagonal, and 0 everywhere else, right? So this is how you define Jordan block for any arbitrary value of k and lambda. Okay. So I should talk about generalized eigenvector first. Then we'll move to some examples of this Jordan canonical form, where we'll actually calculate these generalized eigenvector and Jordan blocks and all, and then it would be more clear to you. Okay. So if you remember, what was the definition for an eigenvalue? So an eigenvalue meant that a lambda, this is AV is equal to lambda V, right? So if you used to take this as lambda I, V equal to 0. Now, if you have insufficient number of eigenvectors, or I would say if you have insufficient number of linearly independent eigenvectors corresponding to lambda, that this property is not satisfied, what you can do is you can look for next power of, okay, next power of this. So rather than power 1 over here, what you did is you look for a minus lambda a square v equal to 0. Okay, and you will keep looking till the point you have an independent thing to your existing eigenvector. Okay, this is the motivation behind generalized eigenvector. So yeah,
Can you please explain what you mean by insufficient eigenvectors corresponding to lambda?
what do I mean by
Insufficient linearly independent eigenvectors corresponding
okay,
to a
I'll
particular
explain
lambda.
that. Okay, so I'll take a very simple example. Let's say you have this matrix, right? So what are its eigenvalues? Eigenvalues are 1 and 1, right? So if you have a lower triangular matrix or an upper triangular matrix, if you have something like this or something like this, then your diagonal elements are always your eigenvalues. Yeah, you can calculate it other ways also. So determinant of 1 minus lambda, 1, 0, 1 minus lambda is 0. So this is 1 minus lambda square is 0, or lambda is equal to 1 comma 1, right? Now, if you look at, if you want to calculate the eigenvector, so what is the multiplicity of your eigenvalues? So your arithmetic multiplicity is 2. Okay. So if you want to diagonalize this matrix A, that is, so if you call this matrix as A, if you want to diagonalize it, then you should have two linearly independent eigenvectors corresponding to lambda equal to 1. If you are able to find two linearly independent eigenvectors, then you will be able to diagonalize your matrix. Okay. Now, if you try to find that is A minus lambda I v is equal to 0, this means that this is lambda is 1 over here. So this is 0, 0, 1, 0, right? v1, v2 is equal to 0. What does this first row mean? First row means v2 is 0, right? So now you have only one independent choice for v1. That means how many linearly independent eigenvectors you can get corresponding to lambda is equal to 1? You can get only one linearly independent eigenvectors. So this is what I mean by not having sufficient number of eigenvectors. That is, your arithmetic mean becomes strictly greater than your arithmetic multiplicity becomes strictly greater than your geometric multiplicity. That is, the number of times your eigenvector is occurring in your characteristic polynomial, you don't have those many numbers of independent eigenvectors. Okay. Was I clear? Whoever asked?
Yes, sir.
Okay. Okay. So what we do in generalized eigenvector, I think we have 20 minutes. I'll just define what is a generalized eigenvector. We will move to examples so that it is more clearer. Okay. So let's say in this example, we had lambda is equal to 1 comma 1, and we were only able to find one eigenvector. So that is 1 comma 0 in this case. Okay. Then what we will do is, so we solved a minus lambda I v is equal to 0 to get one eigenvector. Now what we will do is, let's say this eigenvector was v1. To find the generalized eigenvector corresponding to lambda is equal to 1, what we will do is we will solve 1 minus lambda I v is equal to v1. Rather than 0, now what we are choosing is v1. Okay. So this a minus lambda I would be 0, 1, 0, 0. Again, this, let's call this x1, x2 this time. This is equal to v1, which is equal to 1 comma 0. Okay. Now your first row would mean that x2 is 1, right? And your x1 is independent. So what do we obtain? V2 can be 1 comma 1. Now you can see that your 1 comma and 1 comma 0 are linearly independent. And this is not an eigenvector, but this is a generalized eigenvector. Okay. So rather than equating to 0, you equate it to the previous eigenvectors that you have obtained. Okay. Now, for example, if this had 3 multiplicity, then to obtain one more generalized eigenvector, you could have used a minus lambda I v is equal to v2. Am I clear with this? I skipped a bit of the part because I was discussing that counter example sort of thing. But am I clear how do we calculate generalized eigenvectors?
Yes, sir. This is for eigenvalue which has algebraic multiplicity greater than 1.
Hi, which has more algebraic multiplicity, and you are able to find lesser number of independent eigenvectors. Then you use this thing.
Okay, sir.
Okay. Okay. Now there is a very simple rule in Jordan canonical form. How do we calculate Jordan canonical form? You will do exactly same as you do for your eigenvalue and eigenvector. Okay, but now your this Jordan block will have a special structure. Okay, so how does the Jordan canonical form look like? So you will have blocks, okay, where you will have some blocks, so jk2, lambda 2, and so on, and everywhere else you will have 0. What are these jk lambda that we just discussed few moments ago? It will be Jordan blocks of this form, okay, that your diagonal elements are 0 and the super diagonals are 1, everything rest is 0. So those kind of blocks you will have at the diagonal positions, and rest everything will be 0. Okay. Now for an particular eigenvalue, how do we decide the size or the number of Jordan blocks that you will have? That depends on these two things. Okay. So the geometric multiplicity will tell you the number of Jordan blocks that you will have corresponding to a single eigenvalue. So let's say if your geometric multiplicity is 3, then you will have 3 Jordan blocks corresponding to one eigenvalue. Okay, we will come to an example, then these things will be clear. And when we talk about algebraic multiplicity, that will give you the total size of the Jordan block. So the sum of these sizes, if you have, let's say, 3 Jordan blocks, and the this arithmetic multiplicity is 5, then the sum of these 3 Jordan blocks, sizes of these Jordan blocks, must be equal to 5. Okay, well, we'll just get to this example. Okay, we'll solve this second example first, then we'll go to the first example. Okay, so in this example okay, let's start with the first one only. So this is the example where we have been asked to put this particular thing in Jordan canonical form. Okay, so what is the first step that we will do? We will find the determinant of a minus lambda I, that is 4 minus lambda 0 1, 2 3 minus lambda 2 1 0 4. Okay, we'll equate this, sorry, this would be 4 minus lambda towards the diagonal also. Okay, this will be equal to 0. Can some of you tell me the eigenvalue? I'll not take the time in calculating the eigenvalue. I'll just use some software to calculate it for me. So that we can cover all 3 examples in the time that we have. The main aim is to show you how do we calculate the Jordan blocks. I'll just open this MATLAB and calculate this eigenvalue for this particular matrix. Okay. So this is eigenvalue of 401 2, 3, 2, and 1, 0, 4. Okay, so this thing says that the polynomial that you will get is lambda minus 3 square into lambda minus 5. Okay, so now we have two eigenvalues. One is 3, another is 5. Its algebraic multiplicity is 2. Its algebraic multiplicity is 1. Now we'll look at geometric multiplicity. Okay, now based on algebraic multiplicity, what we know is the total size of Jordan block. Okay, so the total size for lambda is equal to 3 is 2, and for lambda is equal to 5 is 1. So let's start writing our this Jordan block, right? So for lambda is equal to 5, it is given that the size is only 1 cross 1. So this size that can happen is only 1 cross 1, right? So what would be the Jordan block of size 1 for 5? So we will have 5 at the diagonal element, right? 1 at the super diagonal and 0 everywhere. Because there is only one element, that would mean we will only have 5 at the diagonal element. So the first Jordan block would have 5 over here, right? Okay. Now we will have two size. So the sum of all these Jordan blocks corresponding to lambda 3 will be 2. How many blocks will be there will be decided based on the geometric mean. Okay. Now how do we calculate geometric mean? We have to look at the number of independent eigenvectors. Okay. So let's look at that. So what we have to do is a minus 2. Oh, sorry, this is 3i v is equal to 0. Okay, so let's write this out. Write out this matrix. 4 minus 3 is 1, 0, 1, 2, 0, 2, 1, 0, 1. Okay, so we want this v1, v2, v3 to be equal to 0. If you just row reduce this thing, it is straight away you can see that if you subtract 2 times first row, this becomes 0, this becomes 0. If you straight away subtract this, this becomes 0, this becomes 0. So the equation reduces to 1, 0, 1, 0, 0, 0, 0, 0, 0. v1, v2, v3 is your 0. What does this mean? If you just take this thing, this means that v1 plus v3 is equal to 0. So you have how many independent choices now you have? So you have to decide on 3 variables, and you have only one restriction in form of this equation. So you have 2 independent choices to make. Okay. So how many linearly independent eigenvectors you can get? You can get 2 linearly independent eigenvectors. Okay. So what is the geometric multiplicity for this? This is 2. And this was 1 only because 1 was the only choice, right? So now geometric multiplicity tells you the number of Jordan blocks. So how many Jordan blocks it will have? 3 will have 2 Jordan blocks. And what is the total sum of size that it can have? It can have only 2. So what is the possibility? That it will have 2 Jordan blocks of size 1 and 1. Okay. So it will have 2 Jordan blocks of size 1 and 1. Right. And rest everything will be filled with zeros. So this is 0, 0, 0, 0, 0, 0. So this matrix is sort of a diagonalizable matrix. So when your matrix is diagonalizable, your Jordan canonical form is equivalent to your diagonal matrix. Okay, that we saw just now with this example. So this is how we wrote the Jordan canonical form for this particular matrix. Let's quickly get to the next example, and then I'll ask you if you have any doubts with respect to this. Okay, so this is sort of easy to calculate its eigenvalue because this is an upper triangular matrix. So its eigenvalues are nothing but the diagonal entries, right? So eigenvalues is nothing but 1, 1, 1. So for lambda is equal to 1, what is this algebraic multiplicity? Algebraic multiplicity is 3, and we need to find the geometric multiplicity. Okay. So what is a minus 1 times I V equal to 0. Okay, so this is 0 1 1 0 0 0 0 0 0. This is V1 V2 V3 is equal to 0 0 0. Now again, if you look at this equation, we have a similar thing that we had in the previous example, right? So what we had was that we had only one condition and three variables to choose from. So number of independent choices will be 2. Hence we will get 2 linearly independent eigenvectors, or that would mean the geometric multiplicity is 2. Okay. Now, what does geometric multiplicity tells you? It tells you that there will be 2 Jordan blocks. 2 blocks, and what would be their total sum? Sum of their sizes. Sum of sizes is the algebraic multiplicity, that is your 3. So what are the possibilities of having 2 blocks so that their sizes sum up to 3? So either the first one can be of size 1 and the another one can be of size 2, or the first one can be of size 1 and another one can be of size 2. Okay, so if you write this particular Jordan canonical form, so what is the size of first block? First block is 1. Second block is of size 2. So how does a block of size 2 looks like? So you have 1 and 1 on the diagonal, again 1 on the super diagonal, and 0 everywhere else, right? And this is the matrix that you obtain, right? You fill in 0 everywhere else, and this is the matrix that you obtained. Okay, so this was the first block, this is the second block, right? So this is the Jordan canonical form if you consider this case, that first block is of size 1 and second block is of size 2. If you consider the other way around, so the first block will be of size 2, right? And the second block will be of size 1. So this is the matrix that you will obtain for Jordan canonical form, right? So these are the two possibilities. Now let's do one more thing. Let's find out its eigenvectors. Okay, so V2 plus V3 is 0 and V1 is independent. So for first case, let's take V1 is equal to 1, V3 is equal to, let's take this as 0, V1 is equal to 0. Let's take V2 as 1, then V3 will be minus 1, right? Now, if we take another can be V1 is 1 and other ones are 0. So these are my two linearly independent eigenvectors that I can get, right? Now, as I said initially, that we can write this matrix as S, J, S inverse. Now we have S, right? Sorry, we have J. This is your Jordan form, Jordan canonical form. In order to obtain S, I said that its column will be eigenvectors and generalized eigenvector. Okay. So we have two eigenvectors, but we need a matrix of size 3 cross 3, right? Then only it would be invertible and everything will fit in place. So last position will be filled by your generalized eigenvector. So how do we calculate generalized eigenvector? We'll do, let's call this as V1, V2. Okay, so we can take any one of them. So A minus identity times V is equal to, let's take it as V2. Okay, so this one reduces to, this is 0, 1, 1, 0, 0, 0, 0, 0, 0 times, let's say this is V1, V2, V3. I'm abusing my notations a bit. And this is equal to 1, 0, 0. So what does this gives? This gives that V2 plus V3 is equal to 1, which means you can have a generalized eigenvector of form, let's say this is 0, 1 by 2 and 1 by 2, right? You can have this as a generalized eigenvector. So you can construct your matrix now. So you can construct your matrix S as V1 as your first column, then V3, because this is generalized eigenvector corresponding to V3, and then your V2. And now you had two choices for your generalized, for your Jordan canonical form. So based on how you construct your S, so if you have written V1 and V3 first, right, because V1 and V3 should come together, then you should have a two block Jordan block towards the top and one block towards the end corresponding to V2. If you would had written S in the form, let's say V2 comma V1 comma V3, right, then you would have gone for the upper one, that you took this corresponding to V2 and then a block corresponding to V1 and V3 towards the end. Okay, so this is how you find the Jordan canonical form. Any doubt in this? Then I can just go for one more example after this. Any doubt in this Jordan canonical form? How do we find, or anything?
Sir, in last case, how do we decided that which Jordan block we have to take?
So here, when see this V3 is a generalized eigenvector corresponding to V1. Okay. So whenever we will write our matrix S, these things will come together. Okay. So ये V1 and V3 will combine form a two block, because V1 is a eigenvector and V3 is a generalized eigenvector. So because we were writing this V1 and V3 first as the first two columns, so we will choose the Jordan canonical form where we have this two block on the top, okay, because we are writing it first. In the second case, when we are writing it towards the end, then we will choose the one where we are writing the two block towards the end. Am I clear? Was I clear?
Yes, sir.
Okay. So if there is no doubt, I'll just do one more example. Okay. So here is again a question. I purposely chose where I don't have to calculate the eigenvalues. So again, the eigenvalues here are -1, -1, and -1, right? So now we have to calculate so for lambda is equal to -1, my algebraic multiplicity is 3. Now I have to find the geometric multiplicity, right? So the geometric multiplicity would be a minus -1 I times v is equal to 0, which means that this is plus, this would be 0 minus 1 0 0 0 minus 2 0 0 0. Okay, and this is v1 v2 v3 equal to 0. Now if you look at this, this would mean the first row would mean that my v2 is 0, second row would mean that my v3 is 0. What is left? Only v1 is left to be independent. So how many independent choice I have? I have only one independent choice, right? And that's why I have only one linearly independent eigenvector. What does that mean? I have geometric multiplicity only to be equal to 1. Okay. So what does my geometric multiplicity tell me? Geometric multiplicity tells me the number of Jordan blocks that I can have. So in this case, I will have only one Jordan block of size 3, because the total size should be 3. So how would a single Jordan block of size 3 look? So diagonal entries will have my eigenvalues, that is -1, -1, -1. Super diagonal will have 1 and rest everything as 0. So for this case, my J matrix will look something like this. And to calculate the S, you can calculate the eigenvector, that is 1 0 0 here. So 1 0 0 can be the first your column of S, right? And for rest of the two, you can find the generalized eigenvector. So yeah, you can straight away do that thing. So this is a minus lambda I times v should be equal to your this 1 0 0, right? So this would mean that my v2 in that case is actually minus 1. So you can calculate this, but I'll just sort of calculate this. This is 0, minus 1, 0, 0, 0, minus 2, 0, 0, 0. This is V1, V2, V3. This is 1, 0, 0, right? So the second row would mean that V3 is 0, and the first one would mean that my V2 is nothing but minus 1. So my second generalized actant vector I can get as 0, minus 1, 0, right? Similarly, to obtain the third one, what we can do is we can do A minus lambda I V is equal to 0, minus 1, 0, right? So that would mean that minus 2 times V3 is minus 1, or V3 is half. So my third generalized eigenvector is 0, 0, half. So this way you can construct your S matrix. Okay. So this is what I had for today. Any doubts in whatever I have covered today, you can ask.